This is the second lecture on modern construction materials. In the first one we gave an introduction to the course, we looked at the important considerations in the choice of a civil engineering material. Today we will go into the microstructure and we look at the chemical bonds that are there between different elements and atoms, and we will see what is the link between what happens in the chemical bonding and the material behavior that we see. Most of this you would have studied in high school and the first few years of college, but today we will look at it from the context of the material behavior. So, we will start off with the Mendeleev periodic table, which you have all seen before, and here we see a listing of elements in the order of their atomic number, and they are put into periods and groups. We see that the periodic table, as I said, presents all the elements are that we can identify similarities and differences. The elements are arranged in increasing order of the atomic number from left to right, and we have the horizontal rows which are called periods, vertical columns are called groups. Now, what is of interest is that the elements of a group have the same electronic configuration. That means, the number of electrons in the outer shell of a group are the same and are as the same as the group number. Now, the atomic model has evolved over a long period of time. Dalton in 1803 looked at the atom as an indivisible particle. This has changed a lot. Thomson in 1904 found that the atom had positive and negative charges. Rutherford found that the atom had a nucleus, and then Bohr found that there were energy levels with electrons moving around the nucleus in different shells. In 1926 Schrodinger developed this model further and came up with an electron cloud model, saying that the electron does not have a very specific orbit, but it moves in a certain area, and this gave rise to the electron cloud model. However, we still use the modified Bohr model. Instead of definite orbits for the electrons, we use the term orbital to represent the distribution of the electron within a certain space around the nucleus in the atom. So, in the modern idea of the atom, the electron, instead of having a fixed orbit, is indicated by a probability of the electron occupying any location, and this is given for hydrogen, where we have the electron in different possible locations. These dots you see here around the nucleus is all the different possible places that the hydrogen electron could be in. Now, when we look at different elements, we have different electronic configurations. Here I will put the figures for some of them. We saw hydrogen having a single electron, carbon has 4 electrons in the outer shell, these are the protons and the neutrons. Oxygen, sodium, aluminum, iron, silicon, chlorine, calcium, and argon is a reference for an atom which has 8 electrons in the outer shell, and that is called the octet configuration. And when an atom reaches or has 8 electrons in the outer shell or the octet configuration, we consider it to be stable, that it does not need to bond with any other atom to become stable. the electrons in the outermost shell are called the valence electrons, and as I said, when we have 8 electrons in the outer shell, that is called the octet configuration, and that is a stable configuration. The number of electrons in the outermost shell, that is the valence electrons, determines the valency of an element, that is the number of bonds which can be formed with other atoms. This depends on the valency, and the valency depends on the number of electrons in the outer shell. So, the valency is the number of valence electrons that can be lost or gained to reach the octet configuration. So, valence electrons can either be lost or gained to reach the octet configuration. And from the electronic configuration table, we can find from the last number below each of these element symbols, you find the valence electrons, and therefore, you can find the valency of each of the atoms. So, this gives an idea of the atomic configuration, the electronic configuration, and how possibly the bonds can develop between different atoms. Now, what happens when atoms come together? Initially, when the atoms are far away, you have a weak attractive force between the atoms. When they come closer together, the attractive forces become larger, there is a stronger attraction, but when they are very close to each other, when they are pushed together even further, then there is a repulsive force. And this is given in this diagram, showing on the y axis the potential energy, increasing potential energy, and the x axis gives the distance between the atoms, the interatomic distance. The bottom dash curve is the attractive forces, gives the attractive forces, how they change the potential energy. The top dash line gives the effect of the repulsive forces, that is curve B. The resultant of curves A and B is curve C. This is the resultant of the effects of the attractive and the repulsive forces. Note that both the attractive and repulsive forces act together, and you get this curve as a resultant of that. What we see is that as the atomic distance decreases, the attractive potential energy is more, and then as the atoms are pushed together or come very close to each other, the potential energy increases and the repulsive part of the potential energy also increases. R0 is the point or the interatomic separation when the potential energy is minimum, or the attractive part of the potential energy is maximum. So, when the atoms are far from each other, there is a weak attraction between them. The attractive forces given by curve A increases as the interatomic distance decreases, and when the atoms are very close to each other, a repulsive force forms, and this ultimately balances the attractive force, and when you have very close interatomic distances, the repulsive force is very high. Now, there are 5 types of bonding forces. 3 of them are called primary bonding forces and 2 secondary bonding forces. The primary bonding forces we will see are much stronger than the secondary bonding forces. So, we will look in little bit of detail in each of these cases and see what effects they could have on the material behavior. We start with the ionic bonding with the example of sodium chloride. So, here we have an atom of sodium with 1 electron in the outer shell, chlorine has 7 electrons in the outer shell, and to be stable each of these atoms have to reach the octet configuration. So, in the case of ionic bonding, what happens is the single electron of the sodium atom in the outer shell is lost, what we now have is a positively charged sodium ion, a cation, and this electron is now transferred to chlorine atom and it becomes a chloride anion with that is negatively charged. So, we have a chloride anion, and so that is given figuratively at the bottom. We have sodium with a single electron in its outer shell combining with chlorine, which has 7 electrons in its outer shell, to give us sodium chloride, where sodium now exists as a sodium cation, a positively charged ion, and then you have chlorine which is existing as a chloride anion or a negatively charged ion. So, to summarize, sodium has one valence electron, that means it has a valency of +1. Chlorine had 7 valence electrons, a valency of -1, that is it needs 1 electron to reach the octet configuration. So, by transferring 1 electron from sodium to chlorine, both get the octet configuration. This transfer of electrons changes the neutrality of the atom as such. The sodium becomes positively charged, that means it becomes a cation, and chlorine becomes negatively charged, it becomes a chloride anion. However, the overall neutrality of the material is maintained. Sodium chloride as such is neutral, because it has in all it has the cations and the anions together. So, the overall neutrality of the material is maintained. So, in ionic or electrovalent bonding, what we see is the atom can get the octet configuration either by losing or gaining electrons. An ionic bond is formed when all the bonded atoms reach their octet configurations by either donating or borrowing valence electrons, and this obviously can only occur between atoms of different elements, because this atoms of the same element will have the same valency and an ionic bond cannot form between them. The atoms in the ionic bond are attracted to each other by electrostatic forces, and the strength of the forces and the strength of the bond which develops is given by E sub A times E sub B divided by R, where E sub A and E sub B are the charges of the two atoms that participate in the bond, and R is the interatomic separation. And what we see here is when the interatomic separation is larger, the attractive forces, the electrostatic forces that are keeping them together, decrease. Now, as we said initially, the ionic bond is a strong bond, and the strength of the bond increases when more electrons are transferred from one atom to the other. The strength of the ionic bond increases when 2 or more electrons are transferred, and this strength of the ionic bond is reflected in the properties such as the melting point. The melting point of sodium chloride is about 800 degrees centigrade. It, as we saw already, involves the transfer of 1 electron. That of magnesium oxide is 2640 degrees Celsius. 2 electrons are involved, 2 electrons are transferred in the ionic bond between magnesium and oxygen, and that of zirconium carbide is 3500 degrees Celsius. 4 electrons are transferred in the ionic bond between zirconium and carbon. So, what we see is more electrons transferred, stronger is the bond, and when the bond is strong, the melting point is higher, because more energy has to be put in to break the bond and separate the elements that form the bond. Another feature of the ionic bond is that it is non-directional. The ions in the ionic bond can be are arranged symmetrically. That is, there is no preferential direction of growth of materials that are bonded with ionic bond. You see the same structure in all directions, for example, in this face centered cubic structure. Another type of strong bond is the covalent bond, where atoms are all of the electron acceptor type, that is, they have a negative valency and close to 8 valence electrons. The octet structure is attained by sharing of 2 or more valence electrons between the atoms. So, here instead of the atom transferring the electrons like we saw in the ionic bond, the octet structure is achieved by sharing of the valence electrons between atoms, and this basically happens in bonds involving elements of groups 4, 5 and 6. And if you remember, we said that the group number indicates the number of electrons in the outer shell or the valence electrons. Covalent bonding obeys what is called the 8 minus n rule, where n is the number of electrons, and what we see is the number of nearest neighbors when atoms bond together in the covalent bond is 8 minus n. Let us look at a case of chlorine. Chlorine has 7 electrons in the outer shell, and we find that when 2 atoms of chlorine get together, then a covalent bond is formed, 2 electrons are shared between the 2 atoms, and you have the octet configuration and you have a chlorine molecule. Covalent bonds are directional. We saw already that ionic bonds are not directional, they can form symmetrically in all directions. Covalent bonds are directional. That means that the bond that forms between the atoms should have a particular configuration. For example, we see here in the water molecule, we see that there is an angle of about 105 degrees between the hydrogen oxygen hydrogen configuration within the water molecule. Similarly, when we have a bond between carbon and oxygen, the angle is 180 degrees. That means, we have lengthwise configuration of the molecules in the case of carbon monoxide and carbon dioxide. In the silica tetrahedra, we find that the angle between the oxygen silicon oxygen configuration is 109 degrees. That means that whichever bond that happens with these elements will always have this type of configuration, and this gives rise to a specific shape of the molecule that forms due to covalent bonding. And this is very important, and we will see this later, because this specific type of directionality gives rise to chains and sheets in covalently bonded materials. So, in chlorine, the valence electrons in the outer shell are 7. So, the valence is -1. It has only one neighbor following the 8 minus n rule, 8 minus 7 giving 1. So, that means chlorine needs only one neighbor to be stable. Sulfur occurs in long chains. Sulfur has 6 electrons in its outer shell. So, its valency is -2. The 8 minus n rule gives us a value of 2. So, that means, we see that for each sulfur atom we have 2 neighboring atoms to make it stable. Bismuth has n equal to 5. So, it occurs in long sheets. Carbon can form a 3-dimensional network, the valency is 4. So, it needs 4 neighboring atoms to form a stable system. So, you have a 3-dimensional network with carbon as in diamond. So, as we said, we can have long chains occurring like in polymers, where we have here in polyethylene chain of carbon and hydrogen. The black spheres represent carbon and the blue spheres represent hydrogen, and you find that the angle between the bonds have to be specific because they are directional, and due to this we find that the polyethylene chain can deform, can change its configuration without changing the angle between the individual atoms. So, this can give rise to long chains which can bend and have a certain amount of flexibility. At the bottom right we have a layer of graphite with carbon atoms, and we find that graphite forms in sheets. Within a sheet we have covalent bonds. Now, this sheet is stable enough such that it does not have to react with anything else out of the plane of the sheet. Silica on the other hand has a more of a 3-dimensional network, where we have silicon and oxygen atoms in a 3-dimensional network. Again, the angle between the oxygen silicon oxygen configuration is predetermined or it is fixed. We saw that in the case of carbon, because of the valency being 4, we have a 3-dimensional network, which is a rare case for covalently bonded materials. Diamond is an exception, where we have a 3-dimensional network forming between the carbon atoms. So, to summarize the covalent bond, we find that the covalent bond is saturated by individual atoms, meaning that once you have a covalently bonded material, the molecules do not have to bond with anything else, it is saturated by the individual bonds. For example, in chlorine, when you have a chlorine molecule, there is no extension, there are no other bonds formed beyond what is needed to form the molecule. Similarly, in chains of sulfur, sheets of bismuth, there is no bond between different chains or different sheets. So, these chains and sheets remain independently within the material. As I said before, covalent bonds do not lead to a lot of 3-dimensional structures, the exceptions being diamond and silica, both of which are very strong materials. In the other cases, since there is not much bonding, not a strong bond between the different chains and sheets, generally we find that covalent elements have poor strength. Even though the covalent bond itself is strong, since we do not have a strong bond between the sheets and between the chains, we see that covalent elements have poor strength, the exception being diamond and silica. And because of these long chains and sheets forming and the possibility of them bending while maintaining the directionality, we find that covalently bonded elements leads to chains that can coil in spirals, leading to high elasticity and flexibility, like in the case of rubber. One interesting case of covalent bonding is in carbon nanotubes, where we have a continuous hexagonal arrangement of carbon atoms leading to a tube like structure. So, this is this would be the top of the tube, and these tubes are very strong, they are tiny, but have strength of 10 to 12 times that of steel. These were first prepared in the late 1990s and they were found to be narrower than a human hair, but very strong. We have had some research going on where people have tried to use nanotubes, carbon nanotubes in cementitious materials and other applications civil engineering, but it is still in a nascent stage. What you see here at the bottom is photograph taken off the web, where you see a nanotube bundle. The scale shown is 5 nanometers. So, you see that each of these nanotubes is even smaller than 5 nanometers. Right now, the uses that are being done and in progress look at cables, equipment which require very high strength and flexibility, fabrics for bulletproof vests, and some maybe low friction bearings for micro machines and so on in terms of mechanical applications. The third strong bond is the metallic bond, and this is of consequence to civil engineering, because many of the materials that are very popularly used in civil engineering and in construction in general are metals, and these derive their properties from metallic bonds. Metallic atoms have few valence electrons, that is, they are elements of groups 1, 2 and 3, and cannot bond with themselves covalently. In a metallic structure, we have valence electrons that detach or delocalize from their atoms and move freely between the positive ions. So, instead of having atoms being shared as we saw in the covalent bond, what we have here in a metallic bond is that the valence electrons detach, separate from the atoms and move freely within the metallic crystal between the positive ions. The positive ions or the cations are arranged regularly in the lattice, in the crystal lattice. Lattice, this is the formation of the crystal. The electrostatic attraction between the positive ions and the freely floating negative ions provides the cohesive strength of the material. So, this means that even though there is no bond between two or more atoms specifically, the whole crystal structure is held together by the positive ions that are arranged in a crystal lattice and the negative ions that are freely floating around in a cloud configuration. So, you see that here represented in this diagram. We have the positive ions, the cations of the metallic atoms, all arranged in a certain configuration which makes up the crystal lattice. Around these cations we have the freely floating electrons. The electrostatic forces between the positively charged ions and all the electrons keeps the whole crystal lattice in place and gives rise to a strong bond. This can be considered as a special case of the covalent bond, where the octet structure is attained by a generalized donation of valence electrons, forming a cloud that permeates through the lattice. So, we have a cloud of electrons throughout the crystal lattice that is keeping the bond together. Now, we can have different configurations. What we saw in the previous slide is that the positively charged ions have to be packed together to give the crystal configuration. So, this packing together can occur in different ways, and one such is what is called the 12 coordination, where we have each atom having 12 neighbors touching. So, in one plane we have this atom surrounded by 6 other atoms. Now, when we think of the plane above and below it, we will have 3 atoms touching this particular atom. So, we have 12 atoms touching the one in the middle, giving rise to what we call the 12 coordination, which is a densely packed structure. So, you can imagine that the atoms are all densely packed in this particular configuration. Another configuration which also gives rise to a densely packed structure is the 8 coordination, where each atom has a structure where 8 neighboring atoms are touching it. So, you have here in one plane you have the atom, and on the plane above and below it you have 4 atoms touching this atom denoted here in dark blue. So, here you see how the dark blue atom has 8 other atoms touching it. This is not as closely packed as the 12 coordination, but also gives rise to a dense structure within the crystal lattice. Now, in terms of directionality, the metallic bond is non-directional. The electrostatic attraction is such that between the ions electrons is such that it gives rise to a non-directional bond, and therefore, metallic crystals can grow in 3 dimensions in all directions. So, this is very important, because this gives rise to the fact that we have isotropic properties within the metal. That means, the properties are same in all directions, and we can have different shapes and sizes being built up with a metal. The type of bond and its properties also give rise to the high thermal and electrical conductivity of the metallic bond, its malleability and ductility. The thermal conductivity and the electrical conductivity come about because we have electrons that are freely floating around in the crystal lattice, and when heat and electricity has to be transferred, these electrons have a good amount of mobility within the crystal. So, they can move and transmit the heat from one end of the body to the other. The malleability and ductility comes about because we saw that the crystal arrangement was in sheets that are closely packed, and these sheets later on we will see in more detail can slip on one another. So, this gives rise to both malleability and ductility. Malleability is the ability to create any form needed. Ductility is the ability to strain a lot before failing, that it has a lot of elongation. So, we find that these crystal planes can slip without breaking of many bonds, and this gives rise to malleability and ductility. Also, we find that the metallic bond, due to its nature, gives high reflectivity and opacity to metals. We know that metals are generally shiny, that means they have high reflectivity, that means they reflect light, and they are also opaque, they do not let light through, and this is attributed to the energy absorption by the free electrons and the emission of light when the energy levels fall back. That is, the electrons can absorb energy and give it back. So, this gives rise to the reflectivity. They also do not let the light through the body of the metal, making it opaque. Also, we find that since there is this sort of a loose structure within the crystal, in the sense that there are electrons floating around, there is not a one-to-one bond between the different atoms, the metals form alloys easily or relatively easily. We can mix different metal atoms together to form an alloy. So, these are some of the very important features of the metallic bond that give rise to the behavior that we see later in the metals. So, to summarize, we have looked at 3 types of strong bonds: the ionic bond, the covalent bond, and the metallic bond. In the ionic bond, we had the bond forming by the donation or the capture or the acceptance of electrons. We looked at the example of sodium chloride. Sodium atom loses one electron to chlorine, and we have an ionic bond formed between sodium and chlorine, and we saw that the ionic bond is strong and becomes stronger with more electrons being transferred or exchanged in the process of the ionic bond. The ionic bond also we saw was a non-directional bond, and it gives rise to symmetric structures that can grow in all directions. Next, what we looked at was the covalent bond, where we had the sharing of electrons to form this stable octet structure, and we saw that this was a directional bond. it gives rise to chains and sheaths, except in the case of silica and diamond, where we had a network structure or 3-dimensional structure. And some of the important aspects of the covalent bond is that the covalently bonded materials are generally not very strong, because there is not a strong bond between the sheaths or between the chains. We can have long chains, large sheaths, but they do not bond to each other, like for example in graphite, and that is the reason why we have the sheaths which can slip against each other, and the long molecular chains which can bend when we put some force on it, and the directionality is maintained when they are bending. We will come back and talk about this when we look at the polymer structure later on. Then the third strong bond that we looked at is the metallic bond, which is a special type of the covalent bond, where instead of having specific bonds between the atoms, what we have is a loosely bonded material, in the sense that we have the electrons floating around with the cations in a certain configuration, but the electrons floating around within the crystal lattice, and this gives rise to very special properties that we use a lot in engineering. For example, the malleability and the ductility, where we have the sheaths, the planes within the crystal that can slip, giving it deformability. The metal crystal can deform a lot without breaking, because these sheaths slip against one another. We also have very good thermal and electrical conductivity, because we have these electrons floating around in the crystal structure, and this can transfer heat from one part of the material to the other. We also have, due to the metallic bond, the fact that metals have very high reflectivity and opacity. The electrons absorb the energy and give it back as they fall back to another energy level. So, metals, as we all know, can have very shiny surfaces, they can reflect light back, and they also do not let light through, because you have a compact structure, you have the electrons absorbing the energy and not letting it through. So, these were the 3 strong bonds. We also saw in the introduction that there are 2 weak bonds, and we will talk about it in the next part of this lecture. We will talk about the van der Waals bonds and the hydrogen bond. Both of these are weak bonds, or what they are called as also are secondary bonds, with the strong bonds being called the primary bonds. So, we will take that up in the second part of the lecture. Thank you.